Good morning. This class we are discussing about phenols. Phenols. As you know that the structure of phenol is this is phenol, and the first is classification of phenol. Classification. Based on the number of OH group present in the phenol, phenols are classified into three: monohydric, dihydric and trihydric. So classification of phenols. Phenols are mainly classified into three. First one is monohydric. Monohydric, as the name indicates, monohydric means only one hydroxyl group. Example, of course, our phenol. Then you can see that OH, and in the second position there is a methyl group. That means what is this one? 2-methyl phenol. 2-methyl phenol. 2-methyl phenol. It is known as orthocresol. Orthocresol. Now, another one. You can see that the CH3 group in the third position. 1, 2, 3. What is this one? 3-methyl phenol. 3-methyl phenol, which is known as metacresol. Metacresol. And next one, you can see that okay, here it is OH and CH3 group in the fourth position. Here the CH3 group. What is this one? 4-methyl phenol. Methyl phenol, or it is known as paracresol. Okay, this is the first classification of phenols based on the number of OH group. Phenols are classified into monohydric, dihydric and trihydric. First we discuss monohydric phenols. Monohydric phenol, example is our normal phenol, ordinary phenol. Second one is 2-methyl phenol, which is known as orthocresol. Then next is 3-methyl phenol, which is known as metacresol, and 4-methyl phenol is known as paracresol. So this is the first classification, monohydric phenols. Next is dihydric phenol. Dihydric phenols. So what do you mean by dihydric phenols? The number of hydroxyl group is 2. Dihydric phenol means there are 2 OH groups are present in the phenol. Example, OH. What is this one? Benzene 1, 2, diol. Okay, benzene 1,2 diol, or it is known as catechol. It is known as catechol. Benzene 1,2 diol, or it is known as catechol. Next is OH, and here is OH. What is this one? Benzene 1,3 diol. Benzene 1,3 diol. It is known as resorcinol. This is catechol, and benzene 1,3 diol, which is known as resorcinol. And the next one is OH. What is here? Benzene 1,4 diol. Benzene 1, 2, 3, 4. Benzene 1,4 diol. It is known as phenol. Okay, this is the second classification. Dihydric alcohols. That means there are 2 OH groups. This is known as benzene 1,2 diol, or it is known as catechol. This is 1,3 benzene 1,3 diol, resorcinol, and this is 1,4 diol, benzene 1,4 diol, which is known as quinol. Next is trihydric phenols. Trihydric. Phenols. What do you mean by trihydric phenols? There are 3 hydroxyl groups are present. Okay, so look at here. Example, OH, here is OH, and here is also OH. What is this one? Benzene 1, 2, 3, 1, 2, 3, triol. Okay, this is benzene 1, 2, 3. Triol, which is known as pyrogallon. Pyrogallon. Okay, pyrogallon. Next is OH, and here is OH. What is this one? 1, 2, 3, 4. Benzene 1, 2, 4 triol. Okay, which is known as hydroxyquinol. Hydroxyquinol. What is that? Hydroxyquinol. And the last one. Okay, OH, and here is OH. What is this one? 1, 2, 3, 4, 5. That means benzene 1, 3, 5 triol. Which is known as fluoroglucinol. Okay, these are examples of trihydric phenols. First one is benzene 1, 2, 3. Benzene 1, 2, 3 triol, which is known as pyrogallon. Next is benzene 1, 2, 3, 4. That means benzene 1, 2, 4 triol, which is known as hydroxyquinol. And the last one is benzene 1, 3, 5. Benzene 1, 3, 5 triol, which is known as fluoroglucinol. This is the main classification of phenol. Phenols are classified into 3: monohydric, dihydric, and trihydric phenols. Next is preparation of phenol. Preparation of phenol. First method, number 1, from cumene. Okay, look at here how cumene is prepared. Cumene is prepared by the reaction of benzene with propene in presence of anhydrous FeCl3 or in presence of phosphoric acid H3PO4. Okay, so how cumene is prepared? Cumene is prepared by the reaction of benzene. So look at here, benzene react with the propane, CH3, CH double bond CH2 in presence of FeCl3, or we can use H3PO4, phosphoric acid. So benzene react with this is benzene react with propane in presence of FeCl3 or H3PO4. Okay, look at here what we are getting. We are getting cumene. You can see that this bond, one of the double bonds, this bond breaks from this carbon. That means this carbon is attaching to the ring. So we get a structure like this. Okay, so here it is this carbon, second carbon C. Okay, C, and in that carbon there is H, and here it is CH3, and you can see that this CH2, that CH2 will join with one hydrogen atom is replaced from here. That hydrogen atom will join with this CH2, or you can write it as CH3. This is known as cumene, which is known as cumene. Once again, this bond breaks from this carbon and it will join with here. So CH is attaching. In that CH there is CH3 group. Now here single bond CH2. That CH2 will join with see, you can see that this group is attached by replacing a hydrogen atom from the ring. That hydrogen atom is joining with this CH2 and it will change into CH3. This is known as cumene. Now next step, cumene on oxidation. What is this one? Oxidation. On oxidation oxidation. This is oxidation at 350 Kelvin. 350 Kelvin. You get another compound, that is here you can see that here it is C, and here it is CH3, here also CH3. Now these two oxygen will come in between C and H, so you can write it as this two oxygen. That means O2 means O, and what will happen? This H is here. Okay, that means the two oxygen atom coming in between carbon and hydrogen, you are getting COOH. This is known as cumene hydroperoxide. Cumene hydroperoxide. Cumene hydroperoxide. Okay. So first we are preparing cumene. Cumene from benzene. Benzene react with the propene. In presence of FeCl3 or H3PO4, we get cumene. Cumene on oxidation at 350 Kelvin, we get a structure like this. O2O, that means two oxygen atom will come in between carbon and hydrogen, OOH. You are getting cumene hydroperoxide. Cumene hydroperoxide. Okay, cumene hydroperoxide. Now in the next step, this cumene hydroperoxide on hydrolysis, acid hydro H2O H plus on treatment with the dilute acid, you can see that this ring will be converted to, okay, here it will change into OH, and plus what we get acetone, CH3 CO CH3 CO CH3. This is our phenol, and what is this one? This is acetone. Okay. Now, this method of preparation of phenol is very important because benzene and propane, we get it as a byproduct from petroleum products, or during petroleum refining, we get benzene and propane. Therefore, the availability of benzene and propane is easy because we are getting it from petroleum products. And after you can see that the byproduct forming here, it is acetone. So, acetone is also having a wide range of application in various industries or laboratories. Therefore, this method of preparation of a phenol is important from cumene, because both the raw materials or the reagents required for the preparation, benzene and propane, they are easily available from petroleum refining time. And the byproduct acetone is also having wide range of applications. So this is the first method of phenol. Phenol is from cumene. How cumene is preparing? Cumene is prepared by the reaction of benzene with propane in presence of FeCl3 or H3PO4. Look at here, benzene react with the propane. This carbon is attaching to the ring. Then one hydrogen atom will be replaced. That hydrogen atom will go to this carbon. Then it will change into CH3. That means we get CH. This CH3 and CH2H will also change into CH3. This is known as cumene. Then on oxidation, two oxygen atom will come in between carbon and hydrogen. You get cumene hydroperoxide, which on hydrolysis we get phenol. Second method. From benzene sulfonic acid. Second method, preparation of phenol from benzene sulfonic acid. Benzene sulfonic acid. How you are preparing benzene sulfonic acid? This all you know very well. Benzene react with fuming H2SO4. Fuming H2SO4. What do we get? We get benzene on the ring. What we will get? SO3H. SO3H. This is known as benzene sulfonic acid. Benzene sulfonic acid. Benzene sulfonic acid ring, SO3H, which is known as benzene sulfonic acid. This benzene sulfonic acid on reaction with NaOH followed by treatment with water, or you can say when benzene sulfonic acid is treated with aqueous NaOH, we get phenol. Okay, this is the second method. That means benzene sulfonic acid. How we are preparing benzene sulfonic acid? Benzene is treated with the fuming H2SO4. We get one hydrogen atom is substituted with SO3H. Then it is known as benzene sulfonic acid. Which benzene sulfonic acid on treatment with aqueous NaOH will be converted to phenol. So that's all about preparation of phenol. Next is reactions of phenol. Reactions. First we are discussing acidity of phenol. Acidity of phenol. Okay, when we studied alcohol, we have discussed the acidity of alcohol. Similarly, here also we are discussing the acidity of phenol. And as you know very well, any acid can immediately react with metal. So here also you can see that since phenol is having acidic nature, the phenol can react with metals. Okay, look at here. When phenol react with metal, you know that any acid react with metal, what will form? Salt and hydrogen. Similarly, here also you can see that when phenol react with sodium, we get the salt. Or which salt we get? You can see that ONA. Okay, and what will be replaced? Hydrogen atom is replaced, or in a balanced state you can write it as a half H2. Half H2 means H. So you can see that this is the first example in order to show the acidity of phenol. Phenol react with metal will form salt plus hydrogen. What is the name of this salt? Sodium phenoxide. Sodium phenoxide. Okay, second example, as you know very well, acid can react with the base. Similarly, here also you can see that phenol can react with NaOH. Okay, acid react with the base. What will form? Salt and water. Similarly, here also what do we get? Here you can see that the same salt ONA, sodium phenoxide ONA, plus what will form? H and OH plus H2O. Okay. That means sodium phenoxide and water. So here you can see that phenol can react with the metal, phenol can react with the base like NaOH, KOH, etc. or alkali like NaOH, KOH, etc. and what will form? Salt and water. But when we studied when we studied alcohol, we can see that alcohol can react with metal. Of course, it will form salt and hydrogen, but alcohols do not react with alkalis. Alcohols do not react with alkalis. That means phenols are more acidic than alcohol. Phenols are more acidic than alcohol, because that is the reason phenol can react with the alkali. Phenol can react with the alkali, but alcohols cannot react with the alkali. That means alcohols are weaker acid. Alcohols are weaker than phenol. Keep it in mind. Alcohols are alcohol is a weaker acid than phenol, and at the same time, the phenols are not essentially acidic to show litmus paper color change, litmus paper test, or they cannot react with metal carbonate or bicarbonate. Once again, phenols are stronger than alcohols, but weaker than carboxylic acid. How do you know weaker than carboxylic acid? Phenol will not show any color change with the litmus paper. But carboxylic acid can show color change with the litmus paper. It will turn blue litmus paper to red. That means, and the second example is carboxylic acid can react with metal carbonate or bicarbonate and will produce salt plus carbon dioxide plus water. That means carboxylic acid can react with the metal carbonates or bicarbonates, and what will produce? Salt plus water plus carbon dioxide. But phenol will not react with the metal carbonate or bicarbonate. That means phenols are weaker than carboxylic acids. Phenols are weaker than carboxylic acid but stronger than alcohols. Keep it in mind. Okay. And now we are passing to the next point. So one point you have to remember: phenols are stronger than alcohols. alcohols and weaker than carboxylic acids. Carboxylic acid. In what? In their acidic property. Acidic property. Okay. That means phenols are stronger than alcohols. They are stronger acid. Phenols are stronger acid than alcohols, but they are weaker than carboxylic acid. Now, why phenols are stronger than alcohols, or we can in reverse, why alcohols are weaker than phenols? Okay, look at here. In the case of alcohols, you can see that CH3OH in water will change into what will form CH3O minus and H plus. Correct. What do you mean by acid? Any substance which can produce H plus is acid. And of course, since alcohol, example methanol, this is methanol, CH3OH, methanol, in water will produce methoxide ion, CH3O minus and H plus. Similarly, phenol, when phenol, OH, phenol in water, H2O, will produce, what will produce? O minus and H plus, or you can write instead of H plus you can write H3O plus. Okay, because this H plus will be taken by the lone pair of oxygen and it will change into H3O plus, or you can write it as H plus or H3O plus. No problem. Here it will produce H plus. Okay. Now you can see that both alcohol, this is alcohol, and this is phenol. Okay, both can produce H plus ions. See, H plus ions. But we can see that alcohol is weaker than phenol. What is the reason? Why alcohol is weaker than phenol, or why phenol is stronger than alcohol? That means a stronger acid means the species which can immediately remove or which can immediately produce H plus ion, that is stronger. That means when you consider alcohol and phenol, we can see that the availability of H plus ion is easier in the case of phenol. Why? H plus is immediately produced or immediately replaced, or in the case of phenol, but in the case of alcohol, these H plus ions are not immediately free. That means this is weaker than phenol. Now, in the case of alcohol, we can see that this negative charge on the oxygen atom, this is localized. That negative charge is permanently accumulated on oxygen atom. That means there is no way for the delocalization of the negative charge. This negative charge is always on this, staying always on this oxygen atom. It cannot move away from the oxygen atom. Therefore, what will happen? This negative charge will attract back this H plus ion. It will attract back this H plus ion. So, the removal of H plus ion is not easier in the case of alcohol. Keep it in mind. Acid means which have to produce any species which can produce H plus ions. In the case of alcohols, of course, there is H plus ions are produced. But what will happen? The negative charge on the alkoxide ion, will attract back this H plus ion. So what will happen? The removal of H0 plus or H plus becomes difficult. Okay. And in the second case, you can see that in the case of phenol, you can see that this is phenoxide ion, What is happening in the phenoxide ion? This is very important. Phenoxide ion, look at here, phenoxide ion. This is O minus. O minus means what is that? This bond breaks, and the bond pair of electron, is coming to oxygen, and H is going without electron, H plus. That means O minus means it is a pair of electron. Okay, O minus means it's a pair of electron because this bond pair, OH bond breaks and both the electrons are moving to oxygen. Okay, now you can see that this pair of electron will be shifted between oxygen and carbon. Okay. This a pair of electron will be shifted between oxygen and carbon. Therefore, here it will become a double bond. That time, this pi bond will be moved to this carbon. Correct? and you get a resonance structure like this. Here it is, you can see that here it is double bond O. Okay, because the bond is shifted to here. Okay, the pair of electron is shifted to here, and here it will become a double bond. And the same time, this pair of electron is moved to this carbon. That means a pair of electron, and you will get a negative charge. Of course, the other bonds are like this. In the next step, you can see that what will happen. This pair of electron will be shifted between these two carbon, and therefore here it will become a double bond, and this pair of electron will be moved to this carbon. So we get the next resonance structure like this. How it is? Here it is double bond O, and here it will become a double bond. Here is our old double bond. Here it is a pair of electron and with a negative charge. And in the next state, what will happen? This pair of electron will be shifted between these two carbon. That time this pi bond is shifting to this carbon. So we get the next structure like this. Okay, here it is. Okay, and here is double bond, and here is our this double bond, and here is the new double bond, and here you can see that a pair of electron with a negative charge. And in the next state, you can see that this pair of electron will be shifted between this carbon with this, between these two carbon. Simultaneously, what will happen? This bond will go back to oxygen. So we get the structure like this. Okay, here it is like this. Here double bond, here is a new double bond, here it is single bond, and here what will happen? Again, oxygen will get a pair of electron with a negative charge. And in the next step, what will happen? This pair of electron again will come back, and what will happen? The reverse. This pair of this pi bond is shifting to this carbon atom. Therefore, here it will become a pair of electron with a negative charge. That means the reverse order. Okay, this is in this direction. And what will happen here? In the next step, this pair of electron will be shifted to here. Then what will happen? This pi bond will be migrated to here. That means here you can see that this resonance is continuing. By resonance, what is happening? The negative charge on the oxygen atom. This negative charge on the oxygen atom is delocalized. The negative charge on the oxygen atom is delocalized into the ring. Therefore, what will happen? Since this negative charge is not concentrated on this oxygen atom, or you can say since this negative charge is moved away from this oxygen atom, what will happen? The removal of H plus is easier. There is no force of attraction between the negative charge and negatively charged oxygen, and H plus is lesser than that of alcohol. But in the case of alcohol, there is no possibility of resonance, or there is no possibility of delocalization of negative charge. But in the case of phenol, the phenoxide ion can be stabilized by resonance. This ion can stabilize itself by resonance. Therefore, the removal of H plus is easier. This is the reason why phenols are more acidic than alcohols. So keep it in mind. In alcohols, there is no possibility of delocalization of negative charge, but in the case of alcohol or phenols, the phenoxide ion can be stabilized by resonance. Clear? And of course, in the case of alcohol, you can see that this CH3 group is electron pushing group. Of course, it will increase the negative charge on the oxygen. That is also another reason why the removal of H plus is become difficult. Okay, so up to here we are concluding this class, and thank you.